discuss a projectile motion problem about a cannonball being fired at 50 meters per second, but it's being fired at an angle of 40 degrees. And 220 meters to its right is a wall, and the wall is 30 meters high. And the question is asking about whether the cannonball ends up striking the wall or does it clear the wall. And we're going to be using our projectile motion concepts to solve this problem. So the diagram looks something like this. You've got the ground, and then you have a cannonball right here. And the cannonball is being fired at a velocity, an initial velocity of 50 meters per second at an angle of 40 degrees. And 220 meters to its right is a wall. And the wall is 30 meters tall. The wall is 30 meters tall, and the question is, does the cannonball end up striking the 30-meter tall wall, or does it clear the wall? Does it make it above the wall, or does it end up hitting the wall? So this is the idea that I'm going to use. I'm going to use the x and y velocities, because 50 meters per second is a useful number, but what's even more useful is to find out how fast this cannonball is traveling to the right, and how fast is it traveling up. The velocity to the right, I'm going to call this velocity my horizontal x velocity, meaning my initial velocity in the x direction. So I'm going to label it as VIX, velocity, initial, in the x direction. So this is my horizontal velocity. The vertical velocity, I'm going to call it my VIY, velocity, initial, in the y direction. Now keep in mind the horizontal velocity is going to stay the same. It's not going to change because there's no air resistance. We're neglecting air resistance. So there's nothing slowing this velocity down. However, the vertical velocity will change because gravity is going to slow this velocity down as the ball travels upwards, and then at the highest point, the velocity will be zero. The vertical velocity will be zero, and then the ball is going to come down, and its velocity will become negative because it's coming downwards. At all points, gravity is accelerating it down. At every point in this entire pathway, in this problem, gravity is accelerating us down on the vertical axis, on the y-axis. So what I'm going to do is I'm going to try and figure out how long does it take the ball to travel 220 meters sideways. If I can find out the time it takes to travel 220 meters sideways, I'm going to then use that time to figure out where's the ball located on the vertical axis at that specific time. Because if the ball is located on the vertical axis above 30 meters at that specific time, then that means the ball is going to be right here, so it'll clear the wall. However, if at that time the ball is located at a number less than 30 meters, then the ball is going to be located right here, and that means it strikes the wall. So that's the general idea. How do I find the initial velocity in the x direction and the initial velocity in the y direction? Well, this is a right triangle, so I'm going to use cosine theta to find the adjacent side, and I'm going to use sine theta to find the opposite side. So when I use cosine theta, it comes out to be 38.3 meters per second. That's how fast the ball is traveling sideways. It's covering 38.3 meters every second. When I use sine theta, I come up with 32.1 meters per second. So that means that's the initial vertical velocity. It's going to change. It's going to decrease as the ball goes up. The horizontal velocity is not going to change because, like we said, we're neglecting air resistance, so there's nothing slowing the ball down on the x-axis. So, to find out the time it takes the ball to travel sideways 220 meters with this sideways horizontal velocity, I'm going to simply go back to the idea of average velocity. Average velocity is distance over time. Average velocity is total displacement, how much you moved over a certain time interval. The average velocity I'm going to use to figure out how much time it takes to go sideways is the horizontal velocity, 38.3 meters per second. And the reason why I'm using the horizontal velocity is because I'm trying to figure out the time it takes to cover a horizontal distance of 220 meters. So you keep x's with x's, you keep y's with y's, but equations should only have variables from one axis. The displacement is 220 meters, and I solve for the time. Using algebra, take t over 220 divided by 38.3, gives you a time of 5.7 seconds. So that means the ball covers 220 meters sideways in 5.7 seconds. So my next step is to find out where is the ball located on the y-axis at 5.7 seconds. Remember, if it's located at a displacement above 30 meters at 5.7 seconds, then that means in 5.7 seconds the ball has traveled to the right 220 meters and it's traveled above 30 meters, so the ball will be right here. So that means it clears the wall. However, if at 5.7 seconds the displacement on the y-axis is less than 30, let's say it's 15 meters, then that means the ball is going to be located right here, which means it hits the wall. So, how do I find out at a time interval of 5.7 seconds, how do I find out where is the ball located on the y-axis? Well, I'm going to use one of my kinematics equations, the ones that we had derived in class. We derived this equation starting off by the idea of acceleration. Then we incorporated it with the idea of average velocity. Two simple concepts, and we incorporate them together to come up with many different variations on the equations that are possible. So the one that we determined was final displacement is equals to initial displacement plus initial velocity times time plus 1/2 at squared. I'm trying to find out where the ball is located at 5.7 seconds. So I'm trying to find out what the final displacement is. The initial displacement, the ball's on the ground, so I'm going to make that 0. What do I plug in for the initial velocity? Do I plug in 32.1 or do I plug in 38.3? Well, if these are all y variables, I should stick with the y velocities. The y initial velocity, the y vertical velocity is 32.1 meters per second. That'll go in for here. So 32.1 meters per second. The time is 5.7 seconds plus 1/2. The acceleration is negative 9.81 meters per second squared. That's the acceleration of gravity. And once again, the time is 5.7 seconds. You can use 10 meters per second squared, negative 10 meters per second squared, if that makes your math easy. But that's fine. In labs, you definitely use 9.81 meters per second squared because you want a more precise answer. But when you're doing these word problems, it's fine if you use negative 10 meters per second squared. $32.1 times 5.7 gave me 182.97. Plus times a negative gives you a minus. Half times 9.81 times 5.7 squared gave me 159.2. So 182.97 minus 159.2 comes out to be 23.77 meters. So what does that tell me? That tells me in 5.7 seconds the ball traveled 220 meters to the right, and in 5.7 seconds the ball is located 23.7 meters on the y-axis. So where's the ball located? It's somewhere here. So does it strike the wall? Yes, it strikes the wall. Because in 5.7 seconds, it did make it 220 meters to the wall, but at 5.7 seconds, it was located 23.77 meters above the ground, and the wall is 30 meters, so it doesn't clear the wall. So the ball goes up, 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 and it comes down, and it strikes the wall right there. These are called parametric equations. These equations, the word parametric equations means it tells you where a ball is located on the x-axis or on the y-axis at a specific time interval. That's basically what a parametric equation is. And this problem has shown us where the cannonball is located at 5.7 seconds. Where was it located on the x-axis and where was it located on the y-axis? So at 5.7 seconds, it was located 220 meters to the right on the x-axis and 23.77 meters on the y-axis. Future problems will ask you, if you keep everything the same except for the angle theta, can you clear the wall? So a future problem could be, at what angle theta, keeping your initial velocity 50 meters per second, at what angle theta will the ball clear the wall? So keep that in the back of your mind. You may want to start working on that right now to see if you can come up with a solution. At what angle theta will the ball clear the wall? Now those are questions that we'll also discuss in class as we get more and more comfortable with these parametric equations in projectile motion. I hope this was useful, and we shall continue this with another video in a couple of days.